Today's enterprise AI models are processing complex genomic sequences and high-frequency financial data directly inside multi-tenant cloud environments. To shield this highly sensitive data from the cloud providers themselves, architects rely on hardware-based trusted execution environments. Specifically, they use confidential virtual machines, or CVMs, like Intel TDX. This creates a strict hardware boundary, isolating the guest operating system from the underlying hypervisor. And recently, this protection has expanded outward. The secure perimeter now encompasses AI accelerators, specifically NVIDIA's Hopper confidential GPUs. Pairing an Intel CPU enclave with an NVIDIA confidential GPU is widely considered the industry's gold standard for securing data while it's actively in use. Cloud architects look at this hardware barrier and assume they have achieved absolute data sovereignty against any cloud provider intervention. They are wrong. This security model overlooks the Kubernetes orchestrator, the software layer managing these cloud deployments. A Kubernetes administrator retains full API privileges over the infrastructure. They are still sitting squarely inside the trusted computing base. All it takes is a privileged admin executing a single command, kubectl exec, to force entry directly into the confidential VM. Once inside, that administrator operates with root privileges. They have completely bypassed the hypervisor-level hardware protections. From there, they can dump the application's memory. Proprietary model weights, complex financial algorithms, and unencrypted patient records can simply be extracted and exfiltrated. Hardware-based isolation fails if the orchestrator can enter the machine. True data sovereignty requires the total removal of administrative access from the trusted computing base. This requires a shift in how we establish trust. Instead of trusting the virtual machine, a system called EnclaveX defers all trust until the specific machine learning application itself is cryptographically verified. It does this by establishing an independent root of trust, the Configuration and Attestation Service, or CAS. This service exists in its own separate trusted execution environment. It holds the user's strict security policies and the decryption keys for the AI models. The operational rule here is absolute. CAS will never release those secrets across the network without verifiable proof of the application's integrity. By pulling the keys out of the cloud environment entirely, a compromised guest OS no longer grants an attacker access to the actual data. The verification starts at the hardware level. During the initial boot sequence, the physical hardware measures the CVM firmware and the guest operating system to ensure they haven't been tampered with. As part of that process, a custom EnclaveX kernel module is injected directly into the guest OS. Concurrently, the GPU driver queries the attached NVIDIA hardware, verifying the cryptographic state of the confidential GPUs. As the SCONE runtime launches the ML application, the kernel module performs a dynamic measurement to generate a unique hash. This is sent to the CIS. After verifying the quote against its policy, CIS releases the model decryption keys directly to the application. As a final defensive measure, EnclaveX explicitly disables all memory dumping capabilities within the guest OS. Now, if a Kubernetes admin forces their way in with kubectl exec, they find themselves in a locked environment. The application memory is shielded, and the decryption keys remain completely inaccessible. Process-level software isolation solves the orchestrator problem, but we still have to secure the physical hardware boundary where data travels between processors. The CPU and GPU are connected by the PCIe bus. In a zero-trust model, this bus is an untrusted link, highly vulnerable to physical probing or packet interception. Before any data moves, the CPU and GPU trusted execution environments must first negotiate a secure shared cryptographic key using the SPDM protocol. Once that key is established, all input-output data routes through hardware bounce buffers. These force every piece of data into AES 256 GCM encryption before hitting the PCIe link. The data remains encrypted in transit, only decrypting safely inside the destination processor's trusted boundary. Process-level isolation now successfully spans multiple physical processors, completely blinding the host infrastructure to any data in transit. Which brings us to the engineering question. Does injecting process-level software attestation destroy the inference latency of a large language model? To find out, researchers benchmarked an NVIDIA-optimized Llama 3.1 8 billion parameter model running on an H200 GPU. This chart shows output token throughput. We're comparing the standard confidential VM mode in orange and the secure SCONE EnclaveX mode in green. The data reveals negligible variance. Across scaling batch sizes, the difference hovers at under 2%. SCONE achieves this zero overhead profile because it executes system calls synchronously. Rather than double encrypting memory, the runtime simply relies on the CVM's existing memory protections. Securing the architecture at the application level mathematically costs zero additional latency compared to a standard confidential VM deployment. However, looking back at the chart, there is an unavoidable performance gap between the unencrypted native deployment in blue and the secure VM in orange. Depending on the batch size, activating confidential compute modes incurs a throughput penalty ranging from 35